In this video, I give an introduction to probability theory. So what is probability theory? So many times in the real life and also in cryptography, things might go wrong. And we're actually interested in understanding what is the probability that something goes wrong. Or even on the positive side, right? If you're playing the lottery, you would like to understand, is it a good idea actually to play the lottery? What are the chances that I can actually win? And this is exactly what probability theory is asking. For me as a cryptographer, of course, we're always interested in bad events, and therefore we will use this theory quite a lot to analyze the success probability of the bad guy. So to understand probability theory, we will start with an easy example of coin tossing. Everybody knows this game, right? You have the coin where you have either heads or tail. And then when you want to decide on something, you essentially say, look, we're going to toss the coin. And if head comes out, then you have to, let's say, clean up the table. And otherwise, it's my turn. And the intuition there is that this coin should be fair in the sense we both have the same chances of winning or losing. So in general, this game of coin tossing is a very nice example to understand what are the individual components that we need to formalize. So the first thing that we formalize is this random experiment. And this random experiment essentially is exactly the point of we toss the coin. So what are the possible outcomes? Well, the possible outcomes here, as you can see, are heads and tail. And this is what we also call the sample space. So the sample space describes the set of possible outcomes. Here in this concrete case, the sample space is called omega, and we have the two possible outcomes, h and t, for heads and tails. Now, when we are tossing the coin, some event might happen. And this event corresponds to the point or to the thing, what is the actual outcome. So the event essentially is either h or t depending on heads or tail. And if we are considering a fair coin toss, then we are considering the case that both events have the same probability. And therefore the probability of h, that h happens, equals to the probability that t happens, which is 1/2. So what are the applications of probability theory to cryptography? That's actually the point that we are mainly interested in, right? Well, in our case, we're usually considering that an adversary is trying to break the cryptographic scheme, and we want to analyze its success. And this interaction between the adversary and the system is usually modeled in such a game. On the one side, you see the pictorial description, where essentially there is a challenger that interacts with the adversary. And on the other side, you see the corresponding formalization of this game. And this game is nothing else but also a random experiment. And we will analyze the probability of such games very often. So we will go over this formalization in our video about cryptographic games. Now that I hopefully convinced you that probability in theory is definitely needed, let's take a look on how to formalize it. Well, we start with a basic definition, as you can see here. The first of all, the sample space omega, as we discussed before, is the set of all possible outcomes or elementary events. Right, like in the case of heads and tail, this was h and t. And then, on top of this, we will define a probability distribution. And this probability distribution will assign individual events to a certain probability. And this is expressed in the function as you can see here. And when you essentially look at the individual elements, then you will see that all of them, according to our definition, will be greater or equal 0, right? There are no negative probabilities in this case. When you sum them up, the individual events, then essentially the sum of all the probabilities will be 1. And this is expressed with the summation as you can see below. As I said before in the example with the cryptographic games, we often describe an experiment that have different outcomes. And essentially we will call the set of all possible outcomes an event, and we denote this by big sigma. So this is the description of what actually basic discrete probability is. And we will now take a look at certain variants that we often use in cryptography. So very often in crypto, we have the case that certain events are actually independent. And this means that one event does not depend on the other event. And therefore we have to also formalize the corresponding notion. So if we are considering finite discrete probability space and we are considering two events A and B, then we are saying that these two events are independent if the probability that A and B happen equals to the probability that A happens times the probability that B happens. So if this equation holds, then these two events are called independent. And then next we will discuss one thing or one bound that is very important in cryptography. So very often you're faced with a situation where one of two events, or maybe both of them, might happen. But you actually have no clue what the exact probability of the individual events is, or it is sufficient that you can actually upper bound the probability that at least one of them happens. And this brings us to the notion of the amazing union bound. So the union bound essentially is the following. If you have a finite discrete probability space and two events A and B, then you can upper bound the probability that A or B happens by the sum of the individual events. And this can also be generalized to actually sequence of events, say E1 to EL, by simply summing up the individual events. So in cryptography, very often certain events happen with a very, very small probability. So in general, we call this probability as being negligible, which more or less at this point you can think of it as it doesn't really count. It's too small to be noticeable. And if you use the union bound, then in many cases you can sum up all the different events, and all of the events will have what we call a negligible probability, and therefore the sum of it will also be very, 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 very small. And if this is the case, then we can actually conclude that the scheme is secure. So this bounds helps us exactly in analyzing this situation. You will see this when we come to the part of cryptography and also to the formal proofs, and I hope that this is sufficient as a motivation for now. So very often when we consider probability theory, we are interested in events that are only happening if something happened before. That means an event A, for example, is based on, or is essentially analyzed on the fact that some event B happened before. And conditional probability is exactly analyzing this, and we're discussing now the corresponding definition. Well, we are considering a finite probability space as defined here and two events A and B. And then we are saying that the conditional probability of A given B is defined as follows. And exactly this is the notation that we're using. It is defined as the probability that A and B happens over the probability that B happened. And obviously the probability that B happened cannot be zero, right? Otherwise the value is undefined. Given the definition of conditional probability, this brings us now to the famous Bayes theorem that allows us to compute these conditional probability, and essentially it looks as follows. So we are considering a finite discrete probability space and two events A and B. And we are assuming that the event B does not happen with zero probability, so it's bigger than zero. Then we can compute the conditional probability that A happens given that B happened as follows. First, we are computing the probability of B given A times the probability that A happens over the probability that B actually happened. So now you might want to stop the video for a second and think about why this theorem actually holds. To prove this theorem, what are we going to do? Well, we're actually starting with a definition of conditional probability, which means we can compute the probability of A happening given B as the probability that A and B happens over the probability that B happens. So this is just applying the definition. In the next step, we can actually see that we can swap the ordering of B and A in this AND condition, as this is exactly the same. So by doing so, we didn't change anything. And once we did this, actually, we can replace the definition, as you can also see the lecture notes, of the probability that B and A happens by the probability that B happens given A times the probability that A happens. And this then already concludes the proof of this theorem. So in the following, we are going to take a look at a very important theorem that is known as the law of total probabilities. The law of total probabilities is super useful when you would like to compute the probability of a certain event, but you just simply cannot compute it directly. So to help you understand what's actually going on, let's take a look at the following example. So sometimes we are faced with the following situation. So in this concrete case, we will see that the entire probability space, let's say, consists of this set here. And in fact, we are interested in one event, and let's call this event F. The problem is that we simply have no clue how to compute this F directly. But the nice thing in this situation where we can apply this theorem actually is that we know something about how this probability set is constructed. More precisely, if you take a look at it, then you see that we have here three sets called E1, E2, and E3. And these three sets have the nice property that first of all, they cover the entire space. And the second nice property is that the intersection between E1, E2, and E3 is empty, which means it's a complete partition of all elements there. So if we have this situation, then the law of total probabilities actually tells us how to compute the probability for F as follows. In fact, the law of total probabilities says that we're considering a finite probability space, and we are considering exactly these events E1, E2 to EL. Well, these are the ones that partition the entire space of all possible events, with the property that, well, first of all, the union of them covers the entire space, and second, the intersection between the individual events is in fact empty. And then for any event F, we can essentially compute the probability that the event happens as the sum over the probabilities that F and EI happen. And as you can see in this picture, right, this corresponds exactly to these individual events where F is essentially part of EI. There are several situations in where you're interested in analyzing the probability of a specific outcome. So let's think about the following game where you throw a fair dice twice. As you know, the dice, or the fair dice, essentially has a probability space from 1 to 6, right? These are the possible outcomes. Now let's consider the case where you throw the dice twice. And now you would like to analyze the probability, for example, that the sum of the outcome, which means you essentially take the outcome of your throw and you sum it up, is exactly 12. Which means, what is the probability if I throw a fair dice twice of getting each time 6 at the end? And this process to analyze this outcome, actually, this is where we make use of a random variable. A random variable essentially assigns one event to a certain value. And also in this case, it allows us, for example, to consider or to analyze the case of throwing a dice twice and then assigning the probability to the certain value. So let's take a look at the formal definition. So the definition of a random variable looks as follows. We are considering a finite probability space, and we are essentially saying that the function x going from the probability space to R is called a random variable. Based on this random variable, we are now going to define two things. The first thing is the probability mass function, and the second one is the cumulative distribution function. So in the case of the probability mass function, we're actually interested in analyzing the case that a certain event actually happens. So more precisely, let's think about back to our example of the coin toss, respectively of the dice, of throwing the dice. In fact, we might be interested in analyzing the probability, as we said before, that I'm actually throwing the dice twice and I'm getting exactly the value of 12, right? Like throwing twice a 6. And exactly for this type of analysis, we will use the probability mass function, as we would use what is the probability that the random variable x takes the value 12. The cumulative distribution function is actually quite similar, but in contrast of analyzing one specific assignment, like x2 equals to r, we are interested in analyzing a certain interval, which means we're interested, for example, in analyzing the probability that I'm throwing the dice and I get anything between, let's say, 5 and 12. And this is exactly what the cumulative distribution function does. So if x is a random variable over a finite probability space, then the function f, which maps from r to 0, 1, is defined as fr equals to the probability that x is smaller or equal r, and this is what we call a cumulative distribution function. In many cases, we are interested in understanding what is the expected outcome. For example, if I throw the dice twice, what is the expected outcome that I will actually have? And to analyze this probability, we need the notion of expectation. And this is defined as follows. We are considering a finite discrete probability space, and we are considering a random variable x that takes a value in the set S. Then the expected value or expectation of the random variable x is defined as x of x, and it's computed as the sum over the values of s times the probability that s equals to x, respectively that x takes the value s. Another thing we are often interested in is the question, what is the variance around a certain value? Right? So very often we will have a certain probability distribution and certain events are very likely, but what is the variance there? And this is defined, the variance is defined as follows. Again, we're considering a finite probability space, and we're considering the random variable x in that space. Then the variance var of x is defined as the expectation of x minus the expectation and everything to the squared, which is then computed as the expectation of x squared minus the expectation of x and this value then squared. Finally, I want to present you a very nice theorem that allows us to simplify the computation of the expectation in many cases. So in particular, we might be faced with a situation where we have two random variables, say x1 and x2, and we would like to compute the expectation of x1 plus x2. Then the theorem here essentially tells us that we can compute this expectation by looking at its individual parts. More precisely, if we're considering a finite discrete probability space and two random variables x1 and x2, then the expectation of x1 plus x2 equals to the individual expectations, to the sum of the individual expectations, which means equals to expectation of x1 plus the expectation of x2. Another very nice property of the expectation is that it's linear, which means if we take a scalar and let's call the scalar lambda, then we can essentially multiply or compute the expectation by multiplying the value to the outside. Let me be more precise. So if we want to compute the expectation of lambda times x1, then this equals to lambda times the expectation of x1. So now we are already at the end of this short video. In this short video, we have essentially seen some basics in probability theory that we all need in order to understand and analyze the security and cryptographic games afterwards. So if you like the video, then press thumbs up, and hopefully we will see each other either here again or also in the lecture or maybe at some conference.